Hi, everyone. We're going to get started. If you're still getting coffee, hopefully you can just pay attention. I'm Garima. I'm a grad student at Columbia University.
So Victoria, Owusu Clean Air Fund.
And our session is called Data Collection, Analysis, and Interpretation. And we have four really wonderful speakers. We're going to get started with Ms. Josephine Ndiang'ui from Jomo Kenyatta University of Agriculture and Technology. So Josephine, if you want to make yourself shown.
My name is Josephine Ndiang'ui. I'm a master's student at Jomo Kenyatta University of Agriculture and Technology. I'll be presenting my master's project, part of it, and it involves the monitoring of the diurnal and seasonal variation of ambient particulate matter, PM2.5 in Juja. Next slide. The outline of my presentation will be as follows. We have the introduction, methodology, results, and discussion, and then we'll have the conclusion. Next slide. So for the introduction, we see air pollution is a major issue, and it is strongly linked to urbanization. Strongly linked to urbanization, and I'll be focusing on measuring PM2.5 because it is one of the pollutants that affects human health worldwide. So air quality in Kenya, we see that most of the emissions is from vehicular motor vehicles and mainly from poorly maintained motor vehicles. We also have sources from household sources. This is indoor burning, for example, use of charcoal, kerosene, and wood as a source of fuel for cooking. And then we also have open waste burning as a source of air pollution in cities around Kenya. These sources, they give rise to what we call hotspots, where the levels are much elevated compared to the rest of the part of the cities, affecting low-income neighborhoods and affecting pedestrians, cyclists, and drivers, as well as passengers of matatus. Next slide. So for my research, I'll be focusing on Juja. Juja is in the outskirts of Nairobi. I hope most of you know Nairobi. It's the capital city of Kenya. And why I chose Juja is because it's a growing town. It has a high population, a population of around 300,000 people. And also it is within Kiambu County. Kiambu is the second most populous county after Nairobi. And Juja is located between Nairobi and Thika. Thika is an industrial town. Juja is also located along the busy superhighway, Thika superhighway, as you can see from the photo. It is mostly affected by traffic along that road. And also lastly, for Juja or Kiambu in general, there was no baseline data or data in terms of air quality measurements in terms of PM 2.5 or PM10. Next slide. So for my methodology, I focused on 4 key area types. I wanted to find out the levels of PM 2.5 within these area types. We have institution, roadside, residential, and industrial. From the map, you can see where the sites are located. For the institution, I used where my institute is located within JKUAT. Next slide. So for my instrument, I use the Purple Air 2SD. This is I think a second version of the Purple Air according to the site. It uses laser beam technology and has 2 plant towers, A and B. And to get the measurements of the PM 2.5, you do an average of the 2 sensors to get the levels. It has an internal data storage where you can be able to access the data later on. And then it's a low cost. The cost is about $250. So the reason as to why also I use the purple layer is one, because of data accessibility, the cost, and also it provides real-time data. But for my project, I did not put it on the Wi-Fi. I just connected it on power and Wi-Fi, but I later accessed it using the SD card to analyze the data. Next slide. So for data processing, you clean the data first. The purple layer measures the data after every 2 minutes. So you clean the data first to remove any outliers, and then we average the recordings to 1 hour for every day. And then later, the statistical methods that we used, we had the simple linear regression, we used the same method that was applied by Spinel 2017 to help address the overestimation. Purple layer has a tendency of overestimating the values. So this is one of the major biases of the purple layer. And then we use the R's Pearson correlation coefficient. And also we had the mean absolute error. For analysis, I used R and also Microsoft Excel. Next slide. So before the purple layer is deployed to the sites, we have to first, we collocated first the purple layer with the BAM located at University of Nairobi. This is the nearest reference monitor that was around at the time and was located in Nairobi at the University of Nairobi. It's also good to point out that the weather patterns in Nairobi and Juja are similar, and also the pollutants, the source of pollutants are also similar. So when we did the collocation, we got a correlation of 0.78, mean absolute error of around 5.7, sorry. And after correcting it, next slide, please. After correcting it using the equation that was followed by Spinel, we were able to reduce or improve the accuracy of the purple layer. As you can see, the orange is the raw data, raw purple layer data. The blue is the BAM. We see there's an overestimation, but with the corrected values, it's in the middle. So it's not as accurate as the BAM, but it at least minimizes the overestimation. For the mean absolute error, after applying the correction factor, we achieved a mean absolute error of 3.6 from 5.7, sorry. Next slide. So our results, we were able to compare it, or we compared them with the WHO guidelines. That is the reason as to why it's peaking at around 6. And then we have Kefariti. This is an interesting site. We can see it peaks around 2 a.m. And a few of the residents, when I asked them, they indicated that there's emissions or there's a bad smell during early morning. And I think such a site is very important when policymakers or government agencies, when they're using the reference monitor, as the madam had said, they measure from 6 to 10, but a local sensor is able to calculate or to measure the levels all through or 24 hours. So you're able to also get the measures or the levels also in wee hours of the day or wee hours of the night. So at 2, it indicates that industries in that area have the activities at night. That's why the levels are elevated. So we have the daily mean is around 13, but you can see for the around 2, it's slightly above 40 milligram per meters cubed. 1 minute. Okay, next slide. So here we have the daily average. We have Pine Breeze with the highest and Kifariti with the lowest. And in all the sites, when we calculated, it had a higher PM values compared to the WHO guidelines. Next slide. So for the seasonal variation, we saw JQuat and all the other 4 sites had a difference of where it dropped around 5 to 10 milligram per meters cubed. For the dry and wet, we had 5 to 6 weeks of the measurements in the dry and wet season. When we compared, there was a drop of around 5 to 10 milligrams per meters cubed, where it was higher in the dry season compared to the wet season. Next slide. So for the next slide, we have JQuat. JQuat, we're able to do the measurements for 1 whole year. We're able to see it had a mean concentration, annual mean concentration of 16 milligram per meters cubed, exceeding the WHO guidelines of 5. And then for the seasonal variation, we see that it was higher during June to August compared to October to November. It's also important to see that it was higher during the cooler, dry months or season compared to the hotter, dry season, that is from December to around February. Next slide. Yes. Next slide. So to conclude, PM 2.5 levels in all the 5 sites exceeded WHO guideline of 15 milligram per meters cubed. We were able to establish that vehicular emissions was identified as a key contributor, and also local sensors are crucial for continuous monitoring to be able to identify the hotspots. These are areas that have elevated levels, and also local sensors enhance community involvement that are able to improve on the citizen science. Thank you.
Thank you. Can you please sit here for us? We will be taking questions after the session. Okay. All right. So I'll be introducing the next speaker. He's Mr. Cosmos Wemegah from the University of Energy and Natural Resources.
So I'm Cosmos Wemegah from University of Energy and Natural Resources. So I'm presenting on an algorithm that was used to estimate PM 2.5 from Landsat multi-spectral image. So I will take you through, I'll introduce the course and then some problems that we face, the materials and the methods results, and then some recommendations that I'll make in the conclusion aspect. So we are all aware of the negative impacts of PM 2.5 with a lot of statistics that we've been talking about in terms of health, mobility, mortality, in terms of how it affects the climate, and also the socio-economic development of any country. And Ghana is not an exclusive. So we've been breathing in a lot of pollutants, and we've exceeded the maximum recommendation levels, and most especially within the large cities, this is where it exceeds. So this should inform us that there should be policy actions to curb these problems. Now, the problem that we've been facing over the time is that there's something we call data gap loop. Now, this is where you have the lack of data. There's no data that you use for the analysis to even understand the problem that we have. The data that we have, the network is sparse. And also, if you want to use the satellites, also, we have a low resolution. Now, because there's this gap, it leads to lack of evidence. So there's no evidence because we don't have any data to say that your area is polluted. And because of that, there's lack of awareness, lack of knowledge, and people also assume that they've acclimatized to the problem, so there is no issue. And they are saying this because they don't even have any data to even talk about the issue itself. Now, because there's lack of evidence, then there's lack of policy. Nobody talks about policy because there's nothing to show that you're actually within the problem. And this is as a result of institutional gap, no interest, and also large informal sector. As you came to Accra, you can see that most of our activities are within the informal sectors and they are not regulated as well. And then this leads to a lack of demand for the data. If there is no lack for policy, if there is lack of policy, then people will not also demand for any data, for any research, because there's nothing that you should even look at. If there is institutional gap, then nobody is working together. There's no synergy. So there's no research, there's no institutional synergy. And then it leads back to, again, to create that. Because there's no interest, again, nobody is ready to get any data for the work. Now, how are we going to bridge some of these gaps? And that comes to the objective of this. So we seek to use the Landsat, which is having a high resolution and also covers a large area as well, even in terms of tiles. We are going to retrieve from that the reflectance values from the Landsat visible bands, because the satellites in the atmosphere have spectral cameras, and because the pollutant also reflects lights and disturbs the outgoing and incoming radiations in any way. So if you want to retrieve properties of this, you can use the satellite to do that. And therefore, Landsat is capable of doing something like that. We are going to use the perform the stepwise multiple linear regression for all the bands. And then we'll find the best spectral-based regression model. And then we did some sensitivity tests as well based on the composite band combination. Next slide. So the study area, we use the purple air sensor from the Ghana Air Project, which Professor Kofi Wemegah presented earlier. And those that we used was the one from Accra Central, Ring Road, Roman Ridge, Tetekwashi, Jowlu, Atomic Junction, and then one at Tema. Next slide. So this is how the data flowed. So we have the Landsat visible bands, which we corrected them, we used atmospheric corrections, and then we converted them from the digital numbers to the surface reflectance. And then the purple air sensor also, we applied the correction factor developed by the McFarlane and his group. And then we did the multiple stepwise multiple regression with all the bands as well. And then we evaluated the model. We estimated with some of the data that we have, and then we did some sensitivity test. Next slide. So this is a fair idea of how, when we applied the model to it, this is how it looked like. So you see the hotspot that Professor Kofi Wemegah was talking about, just around this area, is what we see at the down part. That's if we use this legend for detecting them. And then you see that that's the hotspot within the city business district center. Next slide. So once we did the analysis, we also used the Taylor diagram to check which of the models performed better. And we saw that it was the band 1, band 2, band 3 all together. The band 1 is a coastal aerosol, which is also needed for this analysis. So it's including that, it performed better. And then this is the model that we extracted from it. So going forward, when we change the color coding to the recommendation by WHO, we realize that within Accra, most of the areas are very well polluted. And if you look at this compared to that, that's the airport, and you can find some very high emissions from there as well. And this is a color combination of 753, which is very good for monitoring the airborne and then vegetation as well. So we applied it to the whole region to see how PM2.5 varies over the area. And we identified some hotspots. And when we did the combination color composite analysis, we realized that there were some active fire over these areas in the blue, yellow ring, and then some burnt surfaces as well, which could lead to the increase in the emissions that we were receiving from those surfaces. So here too, we could still see there is a band 753, and these are active fire areas with the smoke and plumes coming out in this direction. And then you would see that as it is changing, this composite of 3, 2, 1. So you can see the smoke in the reds as well. And these are areas where we also have the pollutants also being high in terms of the concentration. So it was passing the test as we go along. Next slide. There's the Tawiah area. We also tested within that area, and then we realized that high emissions are also coming from the Harbour area as well with PM 2.5. And then there is a protective area, I think an estuary over there, which was showing very low PM 2.5. But the ocean, you could see that they are very high in the concentrations, and this could be attributed to the sea salts. And then again, there's the Wemegah Dam. This is a salt mine, and then this is the sea. And as it is changing, you will see how the pollutants are also over that area. Now, this is very interesting for the water body to also be having a high pollutant concentration. And this can be also be attributed to some water vapor issues and all that. When it comes to the questions and answers part, I'll be able to answer for you if you really want to know what's going on there. Yes. And also, somebody may think that, okay, within the Accra central area, it is because they are highly built up. That is why it's showing those high emissions. But we tested it also over some villages within the area. And you could see that the villages, the PM 2.5 over there were relatively low or even below the recommendation threshold. And that should tell you that the emissions that comes from the rural areas are not as high as we experience within the urban centers. But then there are some highs that you can see from the arrows there, which are from active fire surfaces with the smoke coming down this way. And that is also contributing to some of the PM 2.5 emissions that we have. And this, if there is any village there, it can affect it. So this one can also help us understand the sources of the PM 2.5 as well. So we've been able to identify an algorithm that we can use to measure PM 2.5 or obtain them from Landsat multi-spectral imaging. And then we have tested it, and it's also proved to be detecting some smokes and then plumes from biomass burning. And then the hotspots also that we identified. And there is a distinct air quality levels between the areas and then the rural areas as well. So there's a lack of ground-based measurement, which can help improve this algorithm and then help us estimate it within areas where we don't have the sensors, and to be able to do further analysis as to how emissions are affecting other communities. Mind you, the local sensors are point source and sometimes may not be able to tell you the sources of these emissions. But once you have a hovering satellite picking up some of these things, you'll be able to identify the sources, and this will help you in terms of the policies that you want to formulate. Landsat is also having a 16-day visiting time. So the temporal resolution is a bit low, and it's challenging when you also have a cloud contamination. But then once you're able to identify clear skies and then use them, you don't necessarily need every day's data to be able to identify some of these sources and then the pollution levels. So this is one-time thing that you can be doing. And then high PM 2.5 detected over water bodies. Are they wrong representations, or there's actually something that is happening with our water bodies as well? Are we getting some emissions from the water bodies? So this, there need to be more studies, especially PM 2.5 relationship between the PM concentrations and water vapor, and also how the water bodies affect the PM concentrations as well. Also, studies must be carried out for different seasons. This was done in in January. So that is within the dry period. So we can test for the wet periods as well to see what kind of algorithm, because the algorithm may not work for different seasons. So you may have to interchange them. And then analyze the composition of pollutants from the water bodies as well. There have been studies that shows that once there's water vapor emissions, it carries some pollutants into the atmosphere and it releases them. So at the surface, near surface emissions, PM 2.5 sources and then water vapor sources are almost the same, but going high up into the atmosphere, the levels reduces with altitude. So this is what we found so far. Thank you. And if you need any questions, if you have any questions after the section, I can answer them for you as well. Thank you.
Okay, thank you, Cosmos. Our next speaker is Dr. Solomon Bililign from North Carolina A&T State University.
I have to make a confession here. When I say low-cost filter collection, it's low cost as far as the filter collection is concerned. But everything else that follows is extremely expensive. So this becomes low cost and attractive only if you have a network of collaborators that work with you. So the message is really, you can do low cost sample collection and get good collaborators and be able to analyze those filters chemically. And so that's one of the points I want to make. And the second point is you can't do this alone. This is a network of collaborations. In fact, I didn't mention most of those here. We have a professor from University of Botswana, University of Science and Technology, UNC Chapel Hill, and University of Genoa in Italy are all involved. So this is a very small portion of a collective work that actually just got submitted to PNAS yesterday. So next slide. Okay, so low-cost sensors provide information on the level of exposure. They are important, we need to know them. But how do we know the chemical composition that really impacts the health? What's in those mixtures that's very critical for impacting health? And also in my lab, we don't only look at the chemical composition, we also try to connect this to optical properties. So we try to look at molecular level absorbance and molecular level composition of those filter samples. And so and what makes this work also unique is because we're looking at biomass fuels all from Africa. So the map shows you the abundance of those fuels. Actually, they were all collected from Botswana and East Africa, and I'm still collecting from all regions of the world to continue the work, including cow dung from East Africa was included in this mix. So and then a mixture of those fuels was also combusted to do the work. So so basically the whole work is based on biomass fuels from Africa. So this is the general experimental setup. I'm not going to go through the details of the setup, but you can see it's not low cost, definitely. And so all the fuels that I take are combusted using a tube furnace. And so one advantage of the tube furnace is that we can change the temperature and we can dial in a specific combustion condition, because the way you combust, whether it's smoldering or flaming or a mixture, has significant implications on the kinds of particles that are emitted. So at low temperatures under smoldering conditions, what you get mostly are organic aerosols, or sometimes called brown carbon. And this is a very vigorous area of study because the optical properties, the radiative impacts have been so much underestimated, and the chemical components of the species are more toxic than ever believed. So that's why we're focusing on smoldering burning. So that's how it combusts inside the furnace. This is a chamber that we put the particles in. We turn the light on, so we look at photo aging, dark aging, and under humidity and dry conditions to simulate the real environment. So the focus is going to be, since I'm looking at molecular level absorbance, we have an AE33 that measures absorption at 7 different wavelengths. And that's the technique that's used to do the measurement. So I'm not going to go into the details of how it works. But the question is, we measure real-time absorption property, and we calculated the mass absorption coefficient using this instrument. And then for the chemical analysis, we use, go ahead, continue. So this is the UNC biomarker spectroscopic facilities. So it's a reversed phase liquid chromatography, diode array detection, so on. So you can read what the instrument is. It's a very sophisticated piece of device. And so it's a facility where we pay per hour to analyze our samples. So for molecular level analysis, we did Teflon samples from each experiment, absorbance and molecular composition of methanol soluble, optimized chromatography, electrospiralization in the positive and negative mode. So we analyzed about 25 selected chamber and 10 ambient fuel filter samples. We had about 100 authentic standards for quantification of brown carbon, and that's more of the detail. And for the filter sampling, this is in Botswana. These are the sites that we chose in Palapai, Botswana, where the Botswana University of Science and Technology is located. So we had a purple air monitor located. We had an AE55 to collect black carbon concentrations. And then we did an online filter, inline filter collection using Teflon filters. And we also used cascade impactors. And the location was in the, I think it's a metrology center in Botswana University. So those are, the simplicity is the fact that we have a Leyland pump that I carry every time I go to different places. I brought it here as well, but my window in the hotel doesn't open, so I cannot install it. I tried to do it here in the yard yesterday. It rained, so my filter is messed up. But everywhere I go, in Addis, in Nairobi, in Botswana, I collect those filters. So that one of the things that one has to be careful about those is they have to be carefully weighed. So we weighed them carefully using a strong balance before I leave. I have to refrigerate every sample that I collect every night. So fortunately, most of the hotels have refrigeration, and I have a refrigeration pack that I use to fly them back to the country. So as long as you are careful about the filter collection, you weigh them carefully, then you can get good results out of those. So this is just some of the results. This is African fuel-derived black carbon mass absorption cross-section. And the dotted line shows for the solid fuels that we collected in Africa, so that's wavelength dependent. And for the other fuels that are mostly savanna grass, cow dung, leaves, and tree branches, it's the absorbance cross-section is a little bit different. And so we are comparing this with what was collected in Switzerland. Next. And this shows you the effect of humidity and aging on the mass absorption coefficient. So as you can see in the first one, the primary emissions, under dry conditions, have very low Mach at shorter wavelengths. But when they are photo-aged, the Mach reduced by 20% at shorter wavelengths and increases to 1.5 times at 450. So this has radiative impacts in climate models. So that's one of them. And then we tried to compare this with existing, this was Saleh in 2020, where he classified brown carbon into very weakly absorbing, moderately absorbing, and strongly absorbing. And what you can see here is that most of the hardwood samples are in the weakly and moderately absorbing side, and most of the grass and cow dung and all those lie within the weakly absorptive slide. Okay, next slide. So this is really the key result, where we measured the mass closure of brown carbon class and contributions to PM. And on the left-hand side, you'll see the different kinds of samples and the conditions under which the filters were collected. And the right-hand side, these are contributions to PM. The color codes indicate the chemical species, coumarins, stibulins, flavonoids, and other speciated species. So I can't read it. So about here in the first one, you have about 2/3 total identified brown carbon mass corresponds to species with matching authentic standards corresponding to coumarins, stilbenes, and flavonoids, and they make up 10 to 20% of the identified brown carbon class. And nitroaromatics are negligible in primary, but contribute up to 30 to 60% upon photoaging and appear in ambient samples, collected in Botswana. And for primary emissions, brown carbon species contribute 7% of the total aerosol mass reduced in presence of relative humidity and photoaging. So we compared broadband mass absorption coefficient, molecular composition of brown carbon, variable depending on fuel type. That's very critical. That's why we need to sample different types of fuels, because there is a strong fuel dependency. We actually identified 182 methanol-soluble brown carbon species, including isomers with diverse polarities, and grouped them into chemical classes quantified using 100 authentic standards with different chromatographic responses. So we are able to identification of the biomass burning source in ambient aerosol and their impact on radiative forcing. So significance is, this is the first quantitative link between real-time light absorbing properties of brown carbon containing organic aerosols and offline molecular composition of brown carbon. This work, I've just submitted it last night to PNAS. And this is a group that I work with, and most of this chemical analysis was done by postdoc Vios Moskos, who is between me and the other lady. And this is the group at North Carolina NT. But what I want to mention is there is another group, Professor Surats and Barbara Turpin at UNC Chapel Hill. And we have Italian colleagues from University of Juja who did some of the work. And Botswana International University, where we had students go every summer to do collecting samples. And Jenica, who is over there next on the other end, is a student who spent 2 months in Botswana to do the sample collection. And with that, I'm fine.
Thank you, Solomon. Last speaker would be Dr. Dan Westerveld from Columbia University.
So my name is Dan Westerveld. I'm a professor at Columbia University and also a courtesy appointment at Mohammed VI Polytechnic University in Morocco. So I'll be talking about a few examples of use cases of well-calibrated low-cost sensors or air sensors, and particularly what are some of the really cool challenges that we can use these things for. So next slide. And I really want to take a moment to acknowledge all the outstanding collaborators and specifically my group members. So you all heard from Garima yesterday, who gave a great talk about some of the work in Ghana. Victoria is here as well, involved in all this stuff. You just heard from Josephine earlier in this session, and I'll be showing some work from some other team members as well. So special thanks to them for everything. Next slide. And also, really can't stress enough how important it is to have, co-produced research with African experts and scholars. And so I don't have time to list everyone's name by orally here, but you can find your name up there. Many of you are in the room. Many of you have also probably attended a capacity building or training event that I organized or led, maybe even here in Ghana a couple of times. Again, very thankful for all of the support and collaboration and co-production of research that we've been able to do together. Next slide. So I'm going to kind of touch on 3 different areas. The first thing is going to be talking about hybrid networks of air sensors and reference monitors. And I'll give a few examples from different parts of the continent. And this part of the talk is going to be mostly highlighting some other work that I've been fortunate enough to be involved in, and that luckily is also work that is featured on these walls in these posters. So this will be a good segue for the next session when we talk about posters. And then I'm going to talk about some exciting work that we're doing in Kinshasa, where we're using air sensors as a tool for attributing sources of pollution. So finding out what are the sources. And then finally, I'll have a couple slides on another use case of air sensors, which I think is very promising, and that's ground truthing the satellite-derived PM 2.5 estimates that a few people have already touched on in this session. Next slide. So this is I'll start here in Accra. This is an example of a co-location that we did with a Purple Air at the U.S. Embassy here in Accra, Ghana. So the U.S. Embassy runs a BAM 1020 reference PM 2.5 monitor. That's me setting up a Purple Air right next to it. We did this in early 2020, so way back in the pre times before the COVID pandemic, which was timely because then we were able to collect a lot of data since then. And so this is the kind of plot we got. So we have PM 2.5 on the y-axis and then month on the x-axis. The purple line is the raw Purple Air data that you would get just out of the box. The turquoise line is the U.S. Embassy BAM 1020 data. And then we can apply a correction factor, which people have talked about a lot yesterday on how to do that. We can apply a correction factor, whether it's a linear regression or machine learning or something like that. And you get the sort of pink line, which now has very low bias for the Purple Air data referenced against the BAM. So you have kind of a high quality data set, and this can then be applied to other Purple Airs throughout Ghana or throughout Accra, at least in this area, as we saw in Cosmos's talk. So next slide. We've also been able to do something a bit similar in nearby Lomé, Togo. And so this is a TOM device and reference monitor that was provided by Africair. And we were able to set this up at the University of Lomé with collaborators, Professor Sabi Koku and Sonla, his master's student, who are in the audience somewhere. And we set up some Purple Airs next to it. This is a picture of Professor Sabi doing that. And the scatter plot I'm showing here is the linear regression, multiple linear regression predicted PM 2.5 from this Purple Air versus the reference. These kind of if we use as a similar environment, Ghana's a lot bigger, so maybe the emission sources are a little bit. Could we use a correction factor from that location and apply it to nearby? The answer is kind of maybe. I mean, the dots are not terribly far from the 1-to-1 line, which is that pink line. But clearly the Lomé correction that we developed with the TOM performs much better. So we're confirming what we would probably expect, that a localized collocation is much better if environment. Next slide. This is some work that you can find way more information about this in Dr. Nana's talk, which is on the wall. But we did a similar thing, work about 15 nodes in Ouagadougou, Burkina Faso, and then a TOM reference monitor at the university. And then we corrected it at all the different sites, and you can see quite high levels of air pollution in this period. This is about 1 year's worth of measurements from the Clarity monitors. You can see levels of 50 or 60 micrograms per meter cubed on average throughout the year. So much, much higher than the WHO standard. Next slide. And then kind of the same thing. I'm sort of repeating myself at this point, but we did this also in Kinshasa with the modulaire made by QuantAQ in the US. And again, you got the scatter plot and then the time series. And Kinshasa, as I'll talk a little more about Kinshasa in the next slides, in a few slides from now, but you'll see it's quite a polluted city currently. Next slide. Yeah, and then I think this might be the last example. This is some work by Moses Njeru from University of Nairobi. So he also has a poster, and we have a clarity network in Mombasa, Kenya. And we were able to co-locate one of the clarity nodes with another TOM, again, provided by the Africair team. And we were able to get some pretty good results on that. So you can check out his paper for more information. Next slide. Okay, so I promised I would talk about Kinshasa here. And so now I'm gonna switch gears a little bit and talk about source attribution. How can we use low-cost sensors or air sensors for source attribution? And so this is data from a QuantAQ modulaire, which is a integrated monitor that has PM1, PM2.5, PM10, the size distribution of particles, and then also a host of gases like CO, NOx, ozone. So what I'm showing here is those gases. The first few plots here on the top are CO, O3, ozone, and NOx. And then on the bottom is the PM2.5. And then we have both a corrected and an uncorrected version of the PM2.5 because there is another BAM 1020 at the US Embassy in Kinshasa, DRC. So the average PM2.5 that we reported was about 40 micrograms per meter cubed. This is over a period in 2022. So this was between May and November of 2022. There was some definitely extreme pollution events. So for example, we see a spike there that is highlighted in the red dashes. That was sort of a daily average in around those days of 70 micrograms per meter cubed. But what we can do here, and others have sort of pioneered this method before me, but they've taken these different time series of gases and particulate matter, and crucially the particle size bin concentrations, and they've thrown that into a non-negative matrix factorization method, which I don't really have time to go into, but it can be used for source identification. It's similar to positive matrix factorization, if you're familiar with that. Next slide. So what we can do is we can use this non-negative matrix factorization to pick out 3 physically interpretable factors. And how do I know 3? Well, you can do some bootstrapping analysis, and you can see which number of factors solution minimizes the error. And in our case, it was 3. So we determined these 3 factors. One was CO dominated. It was dominated by carbon monoxide. So we attribute that to some local secondary particle combustion from vehicles or cooking. It's also associated with larger particles as well. So that's why we think it might be secondary, because there's been aging of particles. The second factor we think is probably also local combustion. So from, small open burning or cooking. But these particles, this factor is dominated by smaller particles. So we think this might be more associated with fresh emissions. And then the third factor we identified, or the third source, is regional biomass burning. So something that comes from, the Congo rainforest, where you have large amounts of fires in different times of year. Next slide. We also leveraged the wind data to help discern the sources. So these devices can be added on a sonic anemometer, which gives you wind speed and wind direction. And those results generally support some of our conclusions about what these factors represent. So factor 1 is associated with lower wind speeds, and also it's associated in the direction, I don't have the map for you, but in the direction of where the major human activities are located in Kinshasa. And so those things together sort of add corroboration to our idea. In the interest of time, I'll keep going here, but there's some other things there that also sort of support our source attribution estimate. Next slide. Okay, and the last thing I'll talk about here, how am I doing on time? We got like a couple minutes. Okay. So I wanted to, the final use case here of sensors that I'm going to present is using them as a ground truthing for getting accurate, high resolution estimates of surface PM 2.5 from satellite data. And so basically this is some work done by Ben Yang, who's a PhD student in my group, and he has developed this method where we can estimate PM 2.5 at 1 kilometer spatial resolution at the surface. So 1 kilometer by 1 kilometer. And so we've applied this over West Africa. So people have done this kind of work a lot over the US and Europe, and I think most of Asia as well, but there hasn't been too much of it, to my knowledge, over Africa. So at heart, it is a satellite-based method. So we take the satellite data and then we train a machine learning model that compares the satellite data with the ground-based monitoring in West Africa. So all of the limitations that Professor Kofi mentioned earlier in his talk about satellite data, those are all relevant here. You know, we only have a one overpass once a day, so we can't have diurnal profiles or anything like that. So those are all, you know, very important things to consider. But I still think that there's some good value here. And because there's so much more ground-based data coming online in Ghana and in other parts of Africa, we now have the ability, I think, to have trust in these machine-learned, satellite-derived estimates of PM 2.5. So yeah, next slide. This is just a sort of proof of concept that it kind of works. So these are various cities across Africa, I think mostly West Africa, where the orange is the PM 2.5 as reported by the satellite. As reported by the satellite plus machine learning method. And then the blue is the various surface-based observations. And they pretty much overlap quite well. You can see the different mean absolute errors. They're pretty low. But the R squared is around 0.7 for most of these. So we think that it's working pretty well, although the more data that we get at the surface, the better. Next slide. And this is just a little bit of a demonstration of what's the power of this. And so we can apply this over a broad area of West Africa, or we can zoom in on Ghana, or we can even zoom in on Accra. And like I said, you can get 1 kilometer spatial resolution in theory. So you can have almost maybe neighborhood or intra-city scale data. And so I've kind of mapped out, like, here's this machine learned satellite prediction overlaid with these red dots, which could be the low cost sensors or the reference monitors. And so you can sort of see how there's some potential here for that. And this is collaboration with the Kintampo Health Research Center at Mount Sinai and the Columbia University School of Public Health. So there's a lot of applications for this. Epidemiological applications, of course, would be huge, but also policy and environmental justice studies. Next slide. So with that, I'll just say that air sensors, when characterized and calibrated against reference monitors, provide really great information. We showed some examples of that. They can also be used for source apportionment, and they can serve as ground truth for PM 2.5 estimates. So I'll stop there and take questions. Thanks.
Okay, thanks to everyone for presentations. Let's have the panelists come up here. And then we have about 20 minutes for questions. We're going to ask that you ask a question and say exactly what speaker you are asking that question for, just to make this more efficient.
My question is to the last speaker. Please, I would like to find out. I thought it was only in Ghana you installed your instrument at the US Embassy. I noticed in Kinshasa also you chose US Embassy. In Ghana, you could have chosen Agbogbloshie or any other heavily polluted area. Why US Embassy? Thank you.
So what I showed there was that was meant to be just a exercise in correcting the low cost sensors. So that site wasn't necessarily chosen as a important source site, because I do agree with you that the US Embassy location is probably less polluted than Agboshi or any of the some of the other sites. So I didn't show any of this in this talk, but Garima's talk yesterday showed some of our locations throughout the city using the Clarity network that we had. And those were kind of all over the place. So it's not just the US Embassy, it's just the reason we pick those is because they often have reference monitors and we can at least develop a correction factor there and then spread that out to the other sites throughout the city.
Yeah, my question goes to the first speaker. Yeah, did you consider, and maybe to Dan as well, do you usually consider the altitude to which you install the purple air? Because it can give you a false positive signal because of, how the particle can be suspended.
Yes, when we're setting up the sensors, I forgot to mention it, we consider the height of where we are placing the sensors. It's usually around the second floor. That's around 5 to 6 meters. Yes.
Hi, Steve Chilgard from Columbia University. To the second speaker, what about the time of day of the satellite? You made this big conclusion that the small communities were low compared to the city, but your satellite flight is a instantaneous estimate, and my guess is that it might vary over the day. So do you take a look at that, or do you take a look at averages of many different flyovers that might be at different times of day? Thank you.
Okay, yes. One thing that I did was I considered different flyovers, which I used in the analysis, but most of them are not shown here, including different seasons. But one thing I also did was when it comes to the PM 2.5 from the purple air, which was used as part of the model, I also averaged, I realized that over the area that is in Accra, the timing is around 10:15 a.m. That's when the satellite mostly pass around. So I averaged within that period of the dry season, 10:15. So I took the sub-daily data from the purple air. Then I averaged them and I also used it. So that's the one that I presented here. So it gives, there was some aggregation for that period. Yeah.
2 seconds. Steve, you're making a great argument for a geostationary satellite over Africa, and that is coming. It might take a decade, but the plans are currently being spun up, so stay tuned.
Yeah, I mean, the 10:15 a.m. time is exactly the issue, because that's not when that community is cooking. So the conclusion of saying that it's very low compared to the city could be misleading.
Well, so what we intend to do now is to check for all those periods and then the times. And then we will look for a long period where we can have all these times within that period. And then also check from the purple air itself. Then we can have either a monthly representation of that using the purple air, using the satellite. And the idea itself is not to get a temporal values of the PM, but to be able to map when it comes to the urban pollution centers. There's one work that we did concerning the urban pollution island and then urban heat island. And there was a synergy between the urban pollution island and then the urban heat island. So that is what is the main idea is coming from. So we are using it for the urban pollution itself.
Okay, thank you. I'm sorry, I will need my colleague, Professor Bertrand, to translate my question, please. It's important for me. My question is for Professor, yeah. Et le travail que nous faisons est un travail scientifique et complexe. Il est difficile de faire l'analyse de la qualité de l'air sur 1 mètre carré sur 5 mètres carrés. Peut-être je n'ai pas bien compris son anglais, mais je voudrais savoir en combien de temps il a pu faire l'analyse de la qualité de l'air pour toute l'Afrique. En combien de temps? Avec combien de capteurs? Comment a-t-il pu recevoir les informations de tous ces pays? En combien de temps il a pu analyser ces informations? Et pour lui, qu'est-ce que ça représente?
Well, Solomon, what he wanted to do to us is how you make your studies and how you collected all the data that you were displaying and how you analyze those data for the entire continent.
No, it's not a representative of the whole continent. This is only a very small sample. So the fuels that we burned in the lab are from Botswana, and the samples on the filters are also from Botswana. So it's only a regional representation. I think that's, so basically what I tried to indicate was the fuels I showed you the abundance of the fuels in different parts of Africa. So they're mostly in the south and in the east. But the analysis was done for a smaller region. But the idea is those filter samples collected in different cities can be compared with lab-generated samples using the same fuels and compare the chemical signatures in both of those. And I believe you don't have to send the samples to the US to do that, because I know there are such laboratories in some of the cities in Africa owned by governments for security purpose or crime analysis and so on. These instruments are available, but they are not used for research purposes. So if you have the link to those connections, I know, for example, for sure in Kampala, I was told there is a place that can do that and so on.
Ma dernière question, c'est pour le professeur Dan. Le professeur Dan a beaucoup accompagné, disons, certains pays de l'Afrique pour l'obtention des capteurs et la formation. Mais qu'est-ce que nous constatons? Avec les difficultés que nous avons pour extraire les données, pour les analyser, on se rend compte qu'au fur et à mesure qu'on progresse, les managers, les fournisseurs de données, plutôt nous bloquent la main. Et cherche maintenant, au lieu du moment où vous parlez de révolutionner les capteurs à faible coût, c'est en ce moment plutôt que vous cherchez des modèles pour rendre plus difficile l'obtention de ces données et l'analyse de ces données. Pourquoi une évolution dans ce sens? Qu'est-ce qui fait ça? Translate it.
For the audience. Well, the issue he's putting here on the table regards the data access to the platforms. He says that sometimes we cannot easily access the data from the platforms. You need maybe a password or you need to pay. And he's saying that with the time, than in the past, it was more complicated to have to access those data. And he doesn't understand why there's been this shift in the negative way, we will say. Because most of us here, we don't have money to pay for the subscription, for instance. And sometimes he said that you need to know maybe a little bit of machine learning in order to access some data. So this is making the data access more complicated for him. Yeah.
Thanks. So I'll respond in English because I'm not confident enough in French. It's a very good point. There's a lot of difficulty in analyzing data, and some of the stuff that I showed in my talk was, it requires a lot of computing resources, a lot of data storage, especially on that satellite stuff. So I think, the biggest thing for me is just more capacity building and more co-production of research, like, having African experts as co-equal partners that are right alongside, doing the research, and, providing the training as well. And so, I didn't go into much of the capacity building work, but a lot of, in addition to the research, I spend a lot of my time on training folks on how to analyze data, how to program in Python or in R. I know there's people in this room here that have seen our presentations on Python and R and things like that. So those are some of the skills that I think folks can try to help with as much as possible to make these data access and data analysis issues easier to deal with.
Thank you very much. Okay.
Yeah, I think what to add to what Dan said, capacity building in terms of not only the infrastructure, but human capacity, training competent technicians and people who can interpret and analyze the data is very critical in making sure what we do in the north is left and continued and sustained in the south. And so those are some kind of efforts that we're trying to build. For example, in Addis Ababa University, I'm an adjunct faculty in the Department of Atmospheric Sciences. We just started the program, a PhD program, just was launched this year. And so I think we engage most of the diaspora community to teach courses and provide seminars and short courses and training to the locals. And I think that's very critical to sustain what is going on.
Thanks, Solomon.
Okay. This may be on a lighter note. Some of the presenters here have said this location is one of the air pollution flashpoints. I'm just wondering why they had to bring us here. Okay, like I said, it's on a lighter note. The first presenter said he was looking at the distribution of pollutants over Accra, and he was sort of looking at sources of these pollutants. I had thought that he would have presented something that would look like a wind rose. That will show direction of wind, because that again will inform where this pollutant may actually be coming from, because he has located a position where there may be fire or something, and has said that may be responsible for the elevated pollution of those areas. Why didn't you consider using wind direction, to do your interpretation?
Okay.
Thank you, Cosmos.
Yeah, so I considered wind direction. I didn't show it here. But if you look at the direction from which the smokes were traveling to, you could see that there were northeasterly winds. And within the period, the dry period, we mostly have these northeasterly winds entering to the south. And that is what was helping the plumes transport to that direction. So if you could, when you see the arrows, all of them were this way. And that's how the winds were traveling into. But the analysis itself was for the Landsat image, just to see how best we could help estimate the PM 2.5 from there. But going forward, a lot of things are going to happen with modeling the integration of winds and all other things. But it was considered.
Good afternoon. Thank you all. I wanted to follow up on the gentleman's question on being technically savvy and being able to understand the data and machine learning and all of that. For the gentleman of North Carolina, you said that you were working with community and doing training in those areas. Can you speak to the type of training and work you're doing with community members to get them to work with data and understand the data?
Solomon.
Yeah, so this is a new initiative that started following a workshop that we had in Kigali last January. So we have tried to establish air quality working groups in 4 East African cities, in Nairobi, Kampala, Kigali, and Addis Ababa. So the Addis Ababa working group is what I generally organize. and it consists of the local EPAs, federal EPAs, health professionals like GeoHealth, and there are people from international community members that are also part of that working group. And the curriculum development was facilitated through the working group. Actually, we have a workshop in December in Addis Ababa, which is organized by London University, and I'm a co-organizer of that to train people on, mostly focused on indoor air quality and child weight birth. So this is more the implications of that. So these are initiatives that started, and so the whole idea is to conduct a full air quality field campaign in selected East African cities, mainly Nairobi and Addis Ababa, in collaboration with the US and UK groups. And for that purpose, you have to make sure the ground-based instruments are well maintained and working properly, and there are people who can sustain the work once the data is collected through those flights, so that the data is not just going back to Europe and America for publication purposes, but for training and policy decisions in those countries. So that's what we're focusing on.
Thank you, Solomon. We are taking the last two questions.
Hi, my question is about what is an ideal height at which a sensor inlet should be placed for an ambient data? Number one. Number two is when you do a co-location, is it quite necessary to have the inlets at the same height for your, for example, your purple layer and the BAM or the other ones, or it could be a different height? And generically, what is a good height for a generic ambient data collection?
So there's a lot of correct answers to this, but I'll say yes, it is important to have the reference monitor and the low-cost sensor at roughly the same height. I wouldn't necessarily get too caught up on making it down to the exact centimeter, but I think that's the better you can get it is good. You know, how high? I mean, I'll let some of the other folks chime in on this as well, but generally you want it to be breathing height or around breathing height if it's an air quality study. But it sort of really depends on your application, I would say.
For my case, that is one of the limitations in terms of the site. Because of the purple layer, you need electricity. So you need to get an area or a balcony where you're able to also access a power socket. So those are one of the factors you also need to consider when setting up the purple layer, what I used. So for my case, I used the 5 to 7 or first floor, second floor. That is what roughly I used. But it is generally dependent on where you can get someone to. For my case, these are people in residential houses. I had to request them to set this purple layer in their house. So you have to just get people who will be accept your to help you set up the sensors. So those are the factors. But generally, I used 5 to 7 meters. Yes, but for the general, maybe other people who've worked with local sensors, they can give their comments.
I have one question for Victoria. From your presentation.
Victoria is here. That is Josephine.
Josephine. Thank you. Sorry. So one question for Josephine. From your presentation, you said low-cost sensor enhance community involvement. I'd like you to expand a bit on that to know how this involvement is to works. And one question for Cosmos. You used the satellite Landsat 8 for your research. I know in some cases Landsat are not good enough for urban areas. So I'd like to know, due to its resolution, even if it's like 15 meters, but so what's the reason you choose to use Landsat 8, not like a Sentinel or others who would have even higher resolution? Thanks.
So for your question, one of the areas I set up the sensor, the one at the roadside, it was actually a student from Jomo Kenyatta doing a bachelor's. And when I told him I want to set up the sensor and I took the gadget, he was very inquisitive of what are you doing? And he didn't charge me. This is a student I didn't know. There are some of the sites are people I know, but this is a student. He didn't charge me. He didn't ask for something in return, but he was just inquisitive of what you're working on, how does it operate, how does the gadget measures dust and all that. So when you're going to set up your sensors, maybe for example in residential areas, people who are focusing on schools, you'll get people who are inquisitive of whatever you're doing, and in that case you'll be able to get maybe people who will be interested later on. For example, in my case, this is let me digress a bit. In high school, there's a lady who came and did a presentation and said she's doing environmental science, and I liked her presentation. When finally I was doing my KCSE, my 4th year exams, when we were selecting courses, I chose environmental science just because of that lady and how she presented herself and how whatever she spoke about and whatever she was doing. So in such cases, when you're going to citizens and telling them what you're doing, you'll get people who will be interested and also come up later on and maybe pick up whatever we are doing. Thank you.
Yeah, so I've been working on environmental challenges in urban areas. One of the works that I presented during the ICAG was urban pollution island and urban heat island synergy. So I wanted to know the interaction. Now, from the analysis, we realized urban pollution island exists in Accra here. And then I wanted to find spatially how it's affecting the area. So that's what led to me trying to implement all these things and then try to extract the PM 2.5 from the Landsat. Now, you were asking, you said it doesn't do well within the urban areas. I didn't apply the panchromatic band to try and get a high resolution. So mine was the 30-meter resolution that I used. So the distortion was not that much. And also, the Landsat is having a thermal band, which you can use to extract land surface temperatures and analyze, especially if you want to do urban heat island. And that I could not get from Sentinel. So this is what I did so that I'll be able to analyze the urban heat island and then analyze the pollution island as well, and then continue to establish the relationship between the two as time goes on. So it's something that I'm working on in a broader area.
Okay, I think that wraps up all of our questions for now. So thank you, Dan, Josephine, Solomon, and Cosmos. And I'm going to hand it back to Tony for the poster session.
Thank you. Thank you for organizing. And thank the speakers too. So we have an announcement.
Hi, everybody. Well, I'm here again this morning just to talk to you about this seminar we are having online next month. That will be on local sensors. But during the seminar, we are going to talk more about the design, how to design and test your local sensors. Since yesterday, we're discussing about how to maintain them. We're talking about capacity building. So this kind of seminar that we are going to host next month will be an occasion for students or for researchers who would like to know how they work, to come and learn how to work. Because sometimes when those sensors get damaged, you need to know how they work, which components are inside, so that you can go also and fix the problem instead of throw it away. So I'm inviting some of you who would like to know more, maybe to attend. Okay, the registration is still open, but the submission is closed already. It's just 2 days, 7 and 8 of November. And we'll be here there again with Dan. We'll be also part of that seminar. So I invite you to join us next month again after this event. So we continue to talk about sensors. Okay, thank you very much.